That's a little bitty engine on a relatively big SUV. It does put out 240 horsepower. Uses an awful lot of technology to do that though. The weirdest thing was when you shut it off and then started it up, the turbo boost worked again for a while. It would stop working when you got on a highway.
Some engines fail because they're old, but others? They were doomed from the moment the blueprint hit the engineer's desk. Today, we're looking at power plants that promised reliability, efficiency, or performance, yet delivered constant breakdowns, massive repair bills, and mechanical nightmares owners never saw coming. If you've ever wondered which engine struggled from day one, buckle up, because we're starting with designs that were flawed, fragile, or fundamentally impossible to keep alive. Number 12. Chrysler 2.7-liter V6. When the Chrysler 2.7-liter V6 arrived in the late 1990s, it was marketed as a modern, efficient engine for sedans like the Dodge Intrepid and Chrysler Concorde. On paper, it looked promising. Lightweight design, decent horsepower, and smooth delivery. But beneath the surface was a catastrophic flaw that would ruin thousands of engines long before they crossed 100,000 miles. The problem wasn't just one weak point, it was a combination of design choices that set the engine up for failure from day one. The biggest issue was oil sludge, and this engine became the poster child for it. The internal passages were too narrow, the crankcase ventilation was poorly managed, and the engine ran extremely hot. All these factors turned the oil into a thick, tar-like sludge that restricted lubrication almost everywhere. Even with perfect maintenance, many owners still faced early engine failure because the design simply couldn't keep itself clean. Once the sludge built up, the timing chain tensioner, water pump, and bearings all started wearing out rapidly. Then came the next disaster, the water pump location. Chrysler mounted it inside the engine, driven by the timing chain. This meant when the pump failed, and it often did, the coolant didn't leak on the ground like a normal car. It leaked directly into the crankcase, mixing with the oil and destroying the engine from within. Many owners didn't even know anything was wrong until the engine seized or spun a bearing. Even routine repairs became a nightmare. Replacing the water pump required major labor, and by the time symptoms appeared, the bottom end was usually already damaged. The engine also suffered from head gasket failures, timing chain problems, and overheating issues that snowballed into complete engine replacement. Mechanics often describe the 2.7-liter V6 as an engine with no margin for error. Miss one oil change? Sludge. Have a slight cooling issue. Overheating. Water pump failure? Total destruction. Even with meticulous care, many units didn't last because the weak foundation couldn't handle real-world conditions. In the end, this engine became infamous across the automotive world. It wasn't just unreliable, it was a design that seemed engineered to fail early, making it one of the most notorious modern engines ever released. Number 11. Toyota 3.0-liter 3VZE V6. It might seem surprising to see a Toyota engine on a list like this, but the 3.0-liter 3VZE V6 was one of the few power plants from the brand that simply missed the mark from the beginning. Used primarily in early Toyota 4Runners and pickups in the late 1980s and early 1990s, it was supposed to offer more power and refinement than the old 22RE. Instead, it became known as an engine that struggled with basic durability, something Toyota engines almost never do. The most notorious flaw was its head gasket failure problem, which was so widespread that Toyota issued a special service campaign to replace head gaskets for free. The root issue wasn't poor maintenance or overheating. It was the gasket material itself. The original design simply wasn't strong enough to handle the heat cycling of the 3VZE. Even engines with low miles and perfect service records experienced gasket leaks that allowed coolant into the combustion chambers. And the failures didn't just happen once. Even after repairs, many engines faced repeat issues because the cooling system often couldn't keep temperatures stable under load. The 3VZE had a cramped engine bay, restrictive airflow, and a combustion chamber design that generated more heat than the cooling system could comfortably manage. All of this added constant stress to an already weak gasket design. Beyond the head gasket issues, the engine had underwhelming performance for its size. With only around 150 horsepower, it struggled to move the heavy 4Runner of the time, especially when paired with the automatic transmission. Owners frequently described it as sluggish, thirsty, and noticeably weaker than competing V6s from Nissan or Ford. And because the engine had to work harder to deliver basic performance, the added stress only accelerated its mechanical problems. The 3VZE also suffered from carbon buildup, timing belt failures, and oil leaks from the valve covers. Getting to certain components required more labor than expected due to tight packaging, making repairs more expensive than they should have been on a mid-1990s truck engine. Mechanics viewed this engine as the rare Toyota mistake. Not catastrophic like some modern turbo failures, but fundamentally flawed in ways that prevented true reliability. It wasn't unusual for these engines to struggle to reach high mileage without major repair work. For many owners, the 3VZE wasn't just disappointing. It felt like an engine that never reached the durability standard associated with its brand, earning its place here as one that was doomed from day one. Number 10. Ford 1.6-liter EcoBoost. The Ford 1.6-liter EcoBoost was introduced with high hopes. It promised solid fuel economy, low emissions, and the punch of a turbocharged engine in a compact package. On paper, it was a breakthrough for Ford's small SUVs and hatchbacks. But in real-world driving, this engine quickly earned a reputation for severe mechanical failures, some of them so dangerous that entire vehicle recalls were issued. From the moment it hit the road, the 1.6-liter EcoBoost seemed to be fighting a losing battle. The most alarming issue was engine overheating. A design flaw in the cooling system allowed coolant to leak from weak points in the cylinder head, especially around the pressurized passages. Over time, this leak didn't just cause overheating, it created a buildup of combustible vapors under the hood. Several documented cases involved engines catching fire while the vehicle was being driven. The problem became so widespread that Ford launched a major recall covering hundreds of thousands of vehicles, including the Escape and Fiesta ST. But overheating was only part of the story. The engine also suffered from turbocharger failures, often caused by inadequate lubrication. The oil feed lines could clog or degrade internally, starving the turbo of oil and causing it to fail prematurely. Once the turbo began to wear out, owners noticed whining sounds, sudden power loss, and, eventually, complete failure that required costly replacement. Then came the issue of cylinder head cracking. The 1.6-liter EcoBoost ran extremely hot, and when combined with thin casting in certain areas, the aluminum head was prone to cracking under load. Once that happened, coolant either vaporized inside the head or leaked into the cylinders, leading to misfires, white smoke, and catastrophic engine damage. Carbon buildup also plagued the engine due to its direct injection design. Over time, intake valves accumulated heavy deposits that caused rough idling, hard starts, and reduced efficiency. Cleaning it required labor-intensive walnut blasting, something most owners never expected on a modern small-displacement engine. Even simple maintenance wasn't simple. Changing the water pump, thermostat, or turbo components required significant disassembly, pushing repair costs far beyond what anyone buying a compact crossover would expect. In the end, the 1.6-liter EcoBoost became one of Ford's most problematic small engines. Despite clever engineering on paper, it suffered from critical weaknesses in heat management, lubrication, and component durability, issues that existed from day one and followed the engine throughout its entire production run. Number 9. Subaru 2.5-liter EJ25. The Subaru 2.5-liter EJ25 is one of the most debated engines in modern automotive history. Some owners claim theirs ran flawlessly for years, but for countless others, this engine became a constant source of repairs, warning lights, overheating issues, and high repair bills. Introduced in the mid-1990s, the EJ25 was intended to be a more powerful evolution of Subaru's earlier Boxer engines. Instead, it became known for one recurring problem so widespread that it defined the engine's entire reputation: head gasket failure. While the EJ25 had several variations over the years, the underlying design placed a heavy thermal load on the gaskets. Subaru's horizontally opposed layout naturally puts the head gaskets low, where heat and pressure accumulate. Combine that with early gasket materials that simply weren't robust enough, and many engines began leaking coolant or oil externally long before they hit 100,000 miles. In some cases, the leak was internal, meaning coolant mixed with engine oil, a guaranteed recipe for eventual bearing failure. The issue wasn't just the gasket itself, it was the entire cooling system layout. Air pockets could become trapped easily, leading to uneven temperatures inside the block. When the engine heated up under load, the aluminum heads expanded faster than the block, stressing the gasket sealing surfaces. The result was a cycle of overheating and gasket deterioration that commonly returned even after repairs. Beyond the gasket problems, the EJ25 struggled with ringland failures, especially in later turbocharged versions. Poor piston design and tight tolerances meant the ringlands could crack, causing oil consumption, knocking, and low compression. Non-turbo versions faced carbon buildup, idle instability, and persistent oil leaks from the cam seals and valve covers. The timing belt system added another layer of risk. With multiple idler pulleys and a water pump driven by the same belt, any failure could result in major damage. Many owners discovered too late that worn pulleys or neglected belts led to catastrophic engine failure. Even with improvements in later years, the EJ25 never fully escaped its reputation. Mechanics often joked that owning one meant planning ahead for at least one head gasket job in its lifetime. For many drivers, the constant overheating scares, coolant smell, and rising maintenance costs overshadowed the engine's otherwise smooth performance. The Subaru EJ25 wasn't the worst engine ever built, but it certainly carried design weaknesses from day one, earning its place here for being an engine that failed far too often, long before its time. Number 8. Cadillac Northstar 5.8. Few engines arrived with as much hype as the Cadillac Northstar 5.8. Debuting in the early 1990s, it was marketed as a technological masterpiece that would bring Cadillac into a new era of high-performance luxury. It featured dual overhead cams, 4 valves per cylinder, and impressive horsepower for its time. But beneath the cutting-edge engineering was a series of design flaws that turned the North Star into one of the most notorious engines Cadillac ever produced. An engine that seemed destined for trouble from the moment it left the drawing board. The most infamous problem was its head bolt design. The aluminum block used relatively soft material for the head bolt threads, and over time, the constant expansion and contraction of the engine caused those threads to pull out. Once that happened, the head gasket could no longer stay sealed. The result? Overheating, coolant loss, and rapid deterioration. Many owners experienced complete engine failure long before 150,000 miles, all because the head bolts couldn't maintain proper tension. Repairing this issue wasn't simple. Mechanics had to install steel thread inserts, known as timeserts, in every bolt hole to fix the engine correctly. The job was expensive, time-consuming, and required specialized tools. For many owners, the repair cost exceeded the value of the entire car. Another serious problem involved oil consumption. The North Star's piston ring design allowed excessive oil to pass into the combustion chamber, especially as the engine aged. Some owners reported using a quart of oil every 500 to 800 miles. This wasn't considered abnormal by Cadillac at the time, leaving many drivers frustrated with constant top-offs and smoky exhaust. The cooling system added even more headaches. The North Star used a complex layout with a pressurized surge tank and several sensors that could trigger limp modes or sudden overheating if anything went wrong. A small leak anywhere in the system could cause the entire engine to run hot. And given the head bolt weakness, overheating usually led to catastrophic consequences. Oil leaks were another constant companion. Valve cover gaskets, half-case seals, and rear main seals were all prone to leaking, some so badly that oil would drip onto the exhaust, producing smoke and strong odors. Despite its smooth performance and strong power delivery, the North Star FIV8 became a cautionary tale. It was advanced but fragile, powerful but poorly executed. For many owners, it wasn't a luxury engine at all, just a high-maintenance nightmare with problems rooted deep in its original design. Number 7. Volkswagen 2.0 TSI Early Gen. The early generation Volkswagen 2.0 TSI engine, especially the EA888 Gen 1 and Gen 2 versions, was supposed to represent the future of VW performance. Turbocharged, efficient, smooth, and packed with modern engineering, it powered some of the brand's most popular cars, including the Passat, Jetta, GTI, and Audi A4. But in real-world ownership, this engine became one of the most problematic small turbo engines ever sold, largely because it carried several major design flaws from day one. The most notorious problem was excessive oil consumption. The early pistons and rings were poorly designed, allowing oil to slip past the ring gaps and burn in the combustion chamber. Many owners reported using a quart every 500 to 1,000 miles, sometimes even more. And this wasn't a wear and tear issue. It happened on relatively new engines, proving the flaw was baked into the engineering. VW eventually redesigned the pistons and rings, but for thousands of owners, the damage had already been done. Then there was the timing chain tensioner failure, one of the most catastrophic issues affecting these engines. The early tensioners were prone to losing pressure or failing completely, causing the chain to skip teeth or snap. When that happened, valves collided with pistons in an instant, destroying the engine. Many cars experienced total engine failure with little or no warning. VW revised the tensioner design, but by that point, countless engines had already met an early end. The carbon buildup problem added even more headaches. Because the 2.0 TSI uses direct injection, fuel never washes over the intake valves. Over time, oil vapors and residues built up into thick, hardened deposits that restricted airflow, lowered performance, and caused misfires. Cleaning required expensive walnut blasting, often needed every 40,000 to 60,000 miles. The PCV system wasn't much better. Early models suffered from PCV valve failures, which caused vacuum leaks, unstable idle, and turbo underperformance. In some cases, a failed PCV valve led to rear main seal blowouts, another costly repair. Turbocharger failures weren't uncommon either. Wastegate actuators often wore out prematurely, causing boost loss, rattling noises, and reduced power. Owners were frequently told they needed an entire turbo replacement. Despite delivering excellent performance and engaging driving dynamics, the early 2.0 TSI simply wasn't durable. It was a modern engine weighed down by fragile components, flawed early engineering, and maintenance demands most owners never expected. It promised excitement, but for many people, it delivered expensive repairs instead. Number 6. BMW N22.0 Turbo. When BMW introduced the N22.0-liter turbocharged engine in 2011, it was intended to replace the naturally aspirated inline-six that enthusiasts loved. On paper, the N20 seemed like a leap forward, lighter, more efficient, and surprisingly powerful for its size. But very quickly, owners and mechanics discovered that the N20 carried a major design flaw that doomed it from the beginning. Weak timing components that could fail long before the engine reached a respectable mileage. The core issue centered around the timing chain, guides, and tensioner, all of which were made from materials that didn't hold up well over time. As the engine accumulated miles, the plastic guides began to wear, crack, or break apart entirely. Once that happened, the timing chain started slapping against the guide rails, creating a rattling noise that many owners described as a death rattle. If ignored, or even if caught too late, the chain could skip teeth or snap, leading to catastrophic engine damage. Even routine driving could accelerate the wear. The N20 ran hot, used thin synthetic oil, and relied heavily on its turbocharger for low-end torque. These factors created more stress on the timing components, which were already underbuilt for the engine's operating environment. In some cases, engines failed before 60,000 miles, leaving owners with repairs costing thousands of dollars. Eventually, BMW issued an extended warranty, tacitly acknowledging that the problem was systemic and rooted in the factory design. The N20 also experienced high oil consumption due to piston ring wear. Because the engine used turbo boost frequently, even in normal commuting, oil control was a challenge. Worn rings allowed oil into the combustion chamber, leading to smoke, fouled spark plugs, and reduced performance. Cooling system issues added another layer of trouble. Water pumps, thermostats, and sensors often failed early, causing overheating. With the N20's tight tolerances and aluminum construction, even a short overheating event could warp the head or damage internal components. Carbon buildup was yet another problem. As a direct injection engine, the N20 was prone to heavy deposits on the intake valves, requiring periodic walnut blasting to restore performance. In theory, the N20 offered modern engineering and great driving dynamics, but in practice, it became known as an engine that demanded constant attention, expensive maintenance, and major repairs far earlier than expected. Its timing system issues alone earn it a clear spot on this list. An engine with impressive potential but fatal flaws baked into its earliest design. Number 5. Chevrolet 2.4-liter Ecotec. The Chevrolet 2.4-liter Ecotec engine was used in a wide range of GM vehicles, from the Chevy Equinox and Malibu to the GMC Terrain and Buick LaCrosse. At first glance, it seemed like a simple, dependable four-cylinder. But over time, this engine developed a reputation for problems so widespread and so persistent that many owners felt it was doomed from the moment it entered production. What made things even worse was that the issues weren't obscure or rare. They were built into the engine's core design. The biggest and most damaging flaw was excessive oil consumption. The 2.4-liter Ecotec used piston rings that didn't provide adequate sealing, especially as the engine aged. The poor ring design caused oil to slip into the combustion chamber, where it burned off without leaving any visible smoke in many cases. Owners often had no idea their engine was running low on oil until it was too late. Some reported needing a quart every 1,000 miles, or even every few hundred miles. Once oil levels dropped, the engine became vulnerable to timing chain wear, bearing damage, and complete failure. Countless drivers experienced blown engines because they unknowingly ran low on oil between service intervals. GM later updated the piston rings and issued service bulletins, but the damage to the engine's reputation was irreversible. Another recurring problem was the high-pressure fuel pump and camshaft actuator system. These components were prone to failure, causing rough idling, hesitation, loss of power, and check engine lights. The variable valve timing actuators relied heavily on clean oil, but with so many engines burning oil rapidly, the system often became starved or contaminated, leading to even more mechanical issues. The timing chain tensioner was also a known weak point. Low oil pressure or degraded oil caused the chain to stretch prematurely, or the tensioner to fail. Once that happened, drivers began hearing rattling noises on startup, an early sign that major engine damage was approaching. Adding to the frustration, many repairs required significant labor. Replacing piston rings or timing components involved extensive teardown, making even common fixes very expensive. To top it off, some versions of the 2.4-liter Ecotec suffered from thermal management issues, causing overheating, coolant leaks, and warped components. When combined with the chronic oil consumption, these engines were vulnerable to rapid wear. In the end, the 2.4-liter Ecotec became known not as a simple and reliable engine, but as one of GM's most problematic four-cylinders, an engine that struggled from the moment it left the factory. Number 4. Hyundai Kia 2.4 GDI Early Years. The early generation Hyundai and Kia 2.4-liter GDI engines, used in models like the Sonata, Santa Fe, Optima, and Sportage, were meant to usher in a new era of efficiency and performance for the brands. With direct injection, modern engineering, and strong fuel economy numbers, the engine looked promising on paper. But once drivers hit real-world mileage, a serious design flaw surfaced. one that caused thousands of engines to fail and eventually led to massive recalls across the United States. The core problem was rooted in the manufacturing process of the crankshaft and connecting rod bearings. During production, metal debris and machining residue sometimes remained inside the oil passages of the engine. This debris restricted oil flow to critical components, particularly the rod bearings. Over time, the bearings experienced accelerated wear or complete failure due to insufficient lubrication. When the bearings wore down, drivers heard knocking sounds, rough operation, and, in many cases, sudden engine seizure. These failures weren't caused by neglect. They were baked into the engine from day one. Even owners who changed their oil early and often were vulnerable because the underlying defect was physical contamination deep within the block. Beyond bearing failure, the 2.4 GDI experienced heavy carbon buildup due to its direct injection design. Without port injection to wash the intake valves, carbon deposits collected rapidly. This caused rough idling, reduced power, misfires, and poor cold starts. Many owners needed expensive walnut blasting long before the engine reached midlife. Oil consumption was another problem. Worn rings, carbon buildup on pistons, and early bearing wear all contributed to oil disappearing faster than expected. For some engines, this led to overheating or catastrophic failure when oil levels dropped too low between service intervals. The oil control rings simply weren't designed robustly enough for long-term use under the engine's high heat conditions. Adding to the frustration, the 2.4 GDI suffered from timing chain tensioner wear, high-pressure fuel pump issues, and problems in the PCV system that increased crankcase pressure. Each of these contributed to the engine's reputation for unpredictability and early breakdowns. The problem became so widespread that Hyundai and Kia extended warranties, launched recalls, and faced federal investigations. These engines weren't just unlucky, they were fundamentally flawed from the earliest stages of production. For many owners, the early 2.4-liter GDI wasn't the efficient modern power plant they expected. Instead, it became a cautionary tale of how manufacturing defects and poor design choices can doom an engine long before it ever hits the road. Number 3. Ford 6.0-liter Power Stroke Diesel. Few engines have earned a reputation as notorious, or as well documented, as the Ford 6.0-liter Power Stroke Diesel. Introduced in 2003 as a successor to the beloved 7.3-liter Power Stroke, the 6.0 was supposed to deliver more power, cleaner emissions, and modern performance for Ford's Super Duty trucks. Instead, it became one of the most problematic diesel engines ever sold in North America. From the moment it hit the road, mechanics knew something wasn't right. The biggest flaw was the engine's EGR, exhaust gas recirculation system. To meet emission standards, Ford adopted a cooled EGR setup that was prone to clogging and overheating. The EGR cooler often cracked internally, sending coolant into the intake system. Once coolant entered the cylinders, it caused white smoke, rough running, and potential hydrolocking. The root issue? The cooler was too restrictive and couldn't handle the soot load produced by the engine. Closely tied to this was the infamous oil cooler failure. The oil cooler had extremely narrow internal passages that easily clogged with debris and sludge. Once this happened, oil temperatures shot up, starving critical engine components of proper cooling. Worse still, when the oil cooler clogged, coolant flow to the EGR cooler was disrupted, making the EGR cooler even more likely to fail. It was a domino effect built into the engine's design. Then came the notorious head bolt problem. The 6.0-liter used only 4 head bolts per cylinder, far fewer than what was needed to contain the high boost pressures from the turbocharger. Under heavy load, the head bolts stretched, allowing the head gaskets to blow. Trucks towed, tuned, driven hard. Head gasket failure was almost guaranteed. Many owners ended up installing aftermarket ARP head studs just to keep the engine running reliably. On top of that, the 6.0-liter suffered from turbocharger vane sticking, faulty injectors, high-pressure oil system leaks, failing sensors, and FICM, fuel injection control module, failures. Each of these was expensive, common, and often connected back to the engine's poor thermal management and overly complex emission system. Despite its strong power and potential, the 6.0-liter Power Stroke quickly became infamous for breakdowns, massive repair bills, and entire fleets of trucks needing engine replacements. Today, it's remembered not for its performance, but for being one of the most problem-prone diesel engines ever installed in a pickup. Number 2. Audi 4.2 V8 timing chain issue. The Audi 4.2-liter V8 should have been a masterpiece. With smooth power delivery, a rich exhaust note, and strong performance in models like the A6, A8, S4, and Q7, it looked like a high-end engine built to last. But hidden deep inside the design was a flaw so costly, so complex, and so widespread that it turned this otherwise impressive engine into a long-term liability. From day one, the 4.2 V8 carried a design choice that doomed thousands of engines. The timing chain was mounted at the back of the engine. Unlike most engines, where the timing chain or belt is at the front for easy access, Audi placed the entire timing system, chains, guides, tensioners, and adjusters, against the transmission bell housing. This made even minor timing component repairs require removing the entire engine from the vehicle. What should have been a standard service became a multi-thousand-dollar operation. But placement was just the beginning of the problem. The chain tensioners and plastic guides wore out far too quickly, especially when exposed to the high heat of the rear-mounted configuration. As the guides wore down, the chain began stretching and rattling on cold starts, a noise many owners soon recognized as the engine's early warning cry. If ignored, the chain could skip teeth, causing severe internal damage. The deeper issue was oil pressure. The hydraulic tensioners relied heavily on stable oil pressure to maintain chain tension, but the 4.2 V8 was known for gradual oil pressure decline due to sludge buildup, worn screens, and varnish formation. This reduced tension, accelerated chain wear, and made cold start rattles even more pronounced. Eventually, many engines reached a point where the entire timing system had to be rebuilt, at a cost often exceeding the value of the car. Carbon buildup was another persistent issue. As a direct injection engine, the 4.2 V8 suffered from heavy intake valve deposits that choked airflow, reduced performance, and created misfires. Cleaning required labor-intensive walnut blasting, and many vehicles needed it repeatedly throughout their lifetime. Oil consumption? That too. Worn valve seals and ring issues caused many owners to watch their oil levels drop between fills, adding another layer of maintenance stress. The tragedy of the Audi 4.2 is that it drove beautifully when new. but its rear-mounted timing chain design and fragile components ensured that long-term ownership was financially painful. For many, it became a luxury engine with a built-in expiration date. Number 1. Mercedes-Benz 1.8-liter M271 compressor. The Mercedes-Benz 1.8-liter M271 compressor engine looked like a winner when it debuted. Compact, supercharged, fuel-efficient, and installed in popular models like the C-Class and SLK, it promised modern performance without the pitfalls of early turbocharged engines. But beneath the badge and engineering prestige, this power plant carried a flaw so fundamental that mechanics quickly learned to identify its symptoms long before owners did. The M271 compressor wasn't just unreliable. It was built on a foundation that struggled from the very first mile. The most notorious weakness was the timing chain and balance shaft gear failure. The M271 used a small, narrow timing chain paired with gears that were cut too softly. Over time, the gears wore rapidly, causing the chain to become loose, rattle loudly, and eventually jump timing. For many engines, this happened well under 100,000 miles, an unacceptable lifespan for a premium brand. When the timing chain stretched, or the gear teeth rounded off, the engine began producing unmistakable rattling on cold starts. Ignore it, and the chain could skip teeth, bending valves, damaging pistons, and resulting in complete engine failure. The repair wasn't cheap either. Replacing the gears and chain required significant labor and often revealed even more internal wear. On top of the timing system issues, the M271 suffered from balance shaft problems that created vibration, poor idle, and accelerated internal wear. The balance shaft sprocket was machined from material that simply didn't withstand long-term stress. Once worn, it caused the engine to run harshly and increased strain on the already fragile timing system. Oil consumption was another constant problem. Many M271 engines burned oil due to worn piston rings, hardened valve stem seals, and PCV system issues. Owners often had to top off oil frequently between service intervals, and low oil levels only made timing chain wear worse. The supercharger clutch added yet another failure point. When the clutch wore out, it caused whining noises, loss of boost, and reduced performance. Replacing it meant removing multiple components, not a simple or cheap job. Electrical issues also plagued the engine. Camshaft position sensors, mass airflow sensors, and throttle bodies frequently failed, causing limp mode, stalling, and hard starts. Individually, these problems would be frustrating. Together, they created an engine with reliability issues baked into its architecture. The M271 compressor promised efficiency and refinement, but instead delivered rattles, oil loss, warning lights, and some of the most expensive repair bills in its class. It wasn't just a flawed design, it was an engine destined for trouble from the moment it left the factory. Some engines fail because of age or neglect, but the ones on this list had trouble built into their DNA from day one. Whether it was weak timing components, poor cooling design, flawed manufacturing, or engineering shortcuts that didn't survive real-world driving, each of these power plants reminds us that not every engine lives up to its promise. Knowing their weaknesses helps you avoid costly mistakes and choose vehicles designed to last, not ones heading toward inevitable trouble the moment you turn the key.